Good morning, everyone, to another day of control system lecture, so to say. To get everyone back up to speed, I want to start the lecture or the lecture block today with a little bit of an introduction in OneNote. So I'm going to draw a couple of things just to remind us what the root locus plot actually is, and because I know this sometimes at the beginning is a little bit strange, right? These curves. Okay, so what did we do last time? We actually introduced the root locus plots. So in German, it's Wurzelortskurve. And we want to do closed loop control design based on that, right? So the goal is to do control design. So far, we didn't do that, right? We discussed some rules, how actually the root locus curves kind of can draw them, right? So what are these root locus curves? So root locus curves or plots, it's basically the same. So root locus curves show all reachable pole locations. And now the important stuff for proportional feedback. So, okay, what does it actually mean? Let's draw a block diagram. Let's say we have a system G of S, right? And now this system, like our espresso machine and aircraft, has some poles somewhere. And usually the goal in control is that you actually want to relocate those poles. And we know if we plug an artificial system, a controller around it and close the loop, we're gonna relocate these poles, right? For example, if G of S, you draw the pole zero map, and let's do this, G of S has these poles, you can use the proportional feedback to move those poles around in a closed loop, right? This is what the root locus curve says, right? So all these points here correspond to a specific proportional gain in your controller where you can place your poles at. Okay, so the question now is, and I tried to emphasize this last time, what happens if we want to have dynamics in our controller? Because we said, okay, see, a pure proportional controller is not always a good idea. We might need integrators to get steady state accuracy and so on. So the question now is, so we cannot visualize controllers with dynamics. Let's say PID controller or PI controller or just a D controller. No, it's not a controller, just an I controller, something like that, right? So the answer obviously is yes, we can. But we need to stick the dynamics of the controller into the plant. But we need okay, let's kind of change color this way. Okay, so let's take on this PD2 system here. Let's do an example. I think it's easier than example. And let's say we have a PD2 system which has a transfer function something like k omega 0 squared s squared plus 2d omega 0s plus omega 0 squared. So a classical PT2 system, right? Okay. And let's see. Take this. So if you draw the pole zero map, so real imaginary part of this guy, it somewhere has poles. Let's do in red, has poles here, right? And you know by now that if you would draw the root locus curve, this guy kind of looks like this. So with negative feedback, you basically can reach these poles here. So, okay, let's say for these poles would I draw and have a damping bigger than 0 and smaller than 1, right? So it's oscillating. So, and our goal should be by the controller increase the damping. So we clearly see if we just do proportional feedback, and we know that, right? We have seen it, we are actually just increasing the frequency and decrease the damping. So with a pure proportional feedback, we are not able to increase the damping with our controller. We have seen it with the espresso machine, right? Remember, you turned up the gain and it started oscillating like hell, right? If you made it too big, it actually got unstable, right? This PD2 system never gets unstable because you cannot make the gains, the locus curve does not cross over to the right half plane. This is a specialty of a PD2 system. Same goes for PD1. But the espresso machine, we remember, was a PD3, and a PD3 can go unstable if you make the gain big enough. Okay. Bottom line, we cannot increase the damping. How do we increase the damping? Well, we need to think about a differential part in the controller. So instead of a pure proportional controller, we are actually adding a differential part. We are adding a 0 in our controller. Okay, let's do this. So we know if we apply a PD controller, or let's write it down, what you say, not possible with pure proportional feedback. Okay, but we know if we add a 0 somewhere, let's add it, for example, here, the new root locus curve will look like this. Okay, if you do the rules, you will see that it's somehow gonna meet here, and it's gonna one pole needs to go to the 0, you know that, and the other one goes to infinity. Okay, so this is your new root locus curve. However, this new root locus curve is also for proportional feedback. But what happened to the 0? Well, we added just the 0 to the system, right? So what we actually did is our new system is not this pure PD2 system, it also has a 0. So our new system is basically a PDT2 system. However, the green line is again just for proportional feedback. Okay, let's sketch out what we actually did. We have our system G of S, which is our PD2. We added a 0 here, S plus mu, S minus mu actually. And then we have this proportional feedback here, right? Obviously, I hope you agree that this guy here is our PD controller, right? This is what we designed, but we are free to choose this 0 here. And the root locus curve, what we are drawing is for this system, right? So-called augmented system then. So, and if you draw the root locus curve for this guy, so the G of S and the 0, you're basically coming to that green line, right? And you again have a line for proportional feedback, because you took that zero and you said as an engineer, oh, I need a zero to increase the damping. So you stick it into your system, and you again get a new curve, right? So you moved that curve from the pure PD2 to this line here, right? And now you can say, okay, I can increase the damper, for example, to here, because now I can find a proportional gain. But obviously your controller now has this proportional gain to place these poles here, and it has this zero here. I think it's not that hard. You just need to be aware of that what you're doing here once, right? So you can still have anything in your controller what we had when we designed PID controllers. By canceling, you're just now adding it to your plots, so you're changing the curves, and then when you say, okay, this curve looks good, I can increase the damping, now you compute the gain. So your controller has basically two parts. It has the dynamics you've added, right, to get the curves in the right shape, and then you calculate the gains to place your closed loop poles on a specific point on the new curves, right? This is how the methodology for control design actually works. Okay, so bottom line, what we need to do, or what we need to do in the lecture, say, first we need to understand how to sketch the curve. Well, we did that last time. Right, so right after that we're going to do some example on that, so that you know how to get some practice, yeah, how to sketch them. And then when you know, you basically do it the other way around, right? So usually the control design is not that I give you a system and you compute the gain, right? Usually the locus curve don't go through that point you desire. So what you do first is you add dynamics, and this is where your engineering knowledge needs to come into play, because you need to know if you let's say if you want to have the locus curve further to the left, what are you doing, right? You need to add a pole or a zero or two of those. This is what we need to understand and learn, right? And this is why we need to know how to sketch the curve and what the influence here is. Okay, so and the second point is, with that knowledge then we can add dynamics to the controller. Because this is the actual crucial part of the control design. And the goal is to make the desired pole locations reachable, right? And actually desired closed loop pole location. So let's say if you say, okay, I have that red system and I want that my poles are here somewhere, then you need to understand how you change that green curve, because the green curve needs to go through that point here, because otherwise you cannot place your poles there, right? So this is the first thing. And then you calculate the gain to place it finally there. So this is the very high level strategy how you actually design controllers using the locus curves. And I hope that you kind of understand at this point that we are not really restricted to PID controllers, right? Because you can add here what you like, zeros, poles, so on, right? But usually a PID controller with its two zeros and the integrator is a good starting point. They mostly work, but not always, especially when you have flight control problems where you, for example, consider the structure which can vibrate. Oh, it's going to break. So where the wing can shake, you have like resonance frequency. There, a pure PID controller will probably not work. You can add something to cancel, for example, that, or to shift it. You all can do that with this method, but we're for now sticking to the root locus method only for PID controller, but it's a very general method, so to say, for control design. Okay, so this was the high-level view again, and now we have discussed basically 8 rules, and we're actually going a little bit back, right? We are now at this stage where we say we have a system and we want to understand how do our root locus curves look like for a given system. Only for the proportional feedback. We are not adding dynamics. This is what we're going to do in the second part in the afternoon. In the second part, we will derive a method where we actually understand how and why it makes sense to add a zero. I mean, we know by now that if we want to add damping, we do some stabilization. We know we need zeros in our controllers, right? But the root locus curve gives you another view on that, because it will add some angle and drag these root locus curves to them. Because what you know by now is that the pole in the open loop, when you close the loop, starts to move towards the zero. So if you don't want that your pole goes to infinity, you just place a zero, because you know that then this pole will move to the zero. And thereby, this is the whole idea, thereby you can kind of drag these root locus curves into the direction where you want it. But obviously there's a mathematical method behind it where you can actually place it exactly, so you can reach points exactly and not just like Pi mal Daumen. Okay, so, but I promised you we're going to do some more root locus examples today. Actually, yeah, I hope most of you remember those 8 rules, but yeah, the most important rules will get back in these examples we are doing. I think we stopped at slide 31, but I'm probably going to redo the example on slide 31 just to get, because it's the easiest example I'm showing you. So, okay, so let's hit the start button. So this first example basically is a PD2 system, right? So it's PD2 and it has two real poles. The poles are at -1, -2, right? Here and here. And obviously, usually your job will be to draw that root locus curve, right? But MATLAB does that better, so it's better than I drawing it. I'm showing you the curve already, because it gives you some insight. So first thing you always should do is you look for how many curves you have. Well, we have 2 poles, so the maximum of poles is 2, so we need 2 curves. We have no zeros, so the delta, right? So it's 2 minus 0. We have no zeros, so 2 curves need to go to infinity. And rule number 5, I would say one of the most important rules, not because it's superior than others. Rule number 5 is usually a good starting point, because you need to start somewhere, and this rule is the most, I think I like it the most, because I usually know where to start. And the rule says, okay, look for the odd numbers of poles to your right, and this part of the x-axis then belongs to your root locus curve. Here, when you look from here to the right, you actually have only 1. So this area here needs to belong, blue is probably not the best. Let's go with orange. This area this must belong to our root locus curves, right? This is what rule number 5 says. Okay, we compute the centroid, because we know that the 2 lines go to infinity. This guy. Okay, so we are adding up all the poles. They only have real part, so -1, -2, and we don't have any zeros. And we divide over the number of poles minus the number of zeros. So we get -1.5 is our centroid, and the angles we have are basically, so we go from 0 to 1. So we got 90 degrees and 270 degrees, right? This is what you see here. I think we did that example last time. Yeah. And then you can actually draw the locus curve. From this guy goes here and then goes down, and it's actually it's immediately hitting the asymptotes. We see later that does not be the case. Sometimes they are real asymptotes. Here, the locus curve correspond already to the asymptotes. Sometimes this actually just happens when you go to infinity, but we will see that actually on the next slide. Okay, let's go to this example. Now we have a PD3 system. It's just one more pole now at -3. If you compute the centroid, it's basically straightforward, like same thing as before, -1, -2, -3, and -0, because we don't have any zeros. And we divide that over by 3 minus 2, because we have 3 poles, no zeros, right? If you calculate it out, that is roughly 2. So this is where your centroid is. And 3 curves need to go to infinity because we don't have any zeros, right? Why is the delta here important? Because one root locus curve always ends in 1, 0. When you don't have any zeros, all root locus curves need to go to infinity, because we know there are some zeros there. Okay, so let's go with the angles. The angles are, let's go back to where the equation for the angles was. I think it was somewhere here. Yeah, so you need to go from 0 to basically number of poles minus number of zeros. We don't have any, -1, right? So if you have 3, you go to 2, and you see this is the important stuff here. This equation here really does not have any dependency on the location of the poles. It's just the number of the poles and the number of the zeros. So this guy is really always the same. Whenever you have a delta of 3, your angles are always going to be 60, 180, and 300. Is that right? Plus 120, plus 100. Yes. Right? So the first asymptote starting from your centroid has 60 degree, the next one has 180 degree, and this one has 300. Always the same. When you have a difference of 2, it's always going to be 90 to 70. So this is really, actually, if you do it a couple of times, you actually remember it by heart. Okay, so we've got 3 curves because we have 3 poles, and 3 of those curves go to infinity. And then rule number 5, again, do the checking. We have on the right, we have 0 here, we have 1 here, so this area must belong to this area of the x-axis, or this part of the x-axis must belong to our locus curve. From here to the right we have 2, does not, because it's an even number, and here we have 3, right? So what you see is that if this part of the x-axis is not belonging to the locus curve, this guy only can go right and this guy only can go left. And when they meet, they're going to split up. And here you see that here you're actually approaching the asymptotes when you go to infinity. This guy only can go left, and it goes left to infinity because it also needs to go to infinity, because we have rule number 7. Okay? Okay, so example number 4 is basically, or the next example is not example number 4. The next example is pretty much an extension. What we have is now we have another pole, and we have another pole simply as -4. The centroid is basically -1, -2, -3, -4 over 4, because we have got 4 poles, and the result is -2.5, exactly here. And the angles are 45, 135, 225, and 315, right? Okay, so let's draw the asymptotes. These are these magenta lines here. We obviously have 4 curves, and all of those 4 curves need to go to infinity. If you evaluate rule number 5, pretty straightforward. It ends up being this area of the x-axis belonging to our locus curves. So this guy can only go right, this can go left, and they're going to meet here, and they go up here and approach the asymptotes. Same goes here. Chuck, chuck. Okay, so kind of should be clear. The next part, we've got 3 more examples. Now we're starting to add some zeros to make it a little bit more interesting. I think for purely proportional system which are lagged, right? You see where this is going. So if you add another pole and so on, and yeah, just don't forget what usually sometimes an error comes in with the signs of the poles, right? Because you take the poles positively and you subtract the zeros, and if a zero is in the left half plane, it's negative. Minus gets plus. So don't take a little bit care about that, but otherwise it's actually yeah, pretty straightforward. And the good thing about what I like about the root locus curves is actually that behind that whole thing stands actually a huge mathematical stuff, right? You have basically a Laplace transformed ODEs and so on, but it comes down to actually just drawing some curves, right? So it's actually pretty nice when you think of where we actually came from. Okay, next example is a system which has actually 3 poles and 2 zeros, right? So we've got 3 poles and we've got 2 zeros here. Okay, and what we see is that these poles here, this is a second order model which actually has conjugate complex poles, right? So we compute let's go with rule number 1 first. Okay, so the maximum of the number of poles and the number of zeros is 3, right? This is why we need 3 curves. One curve goes to infinity. Why? Because, well, we've got 3 poles, we've got 2 zeros, the delta is 1. So we know this time only one curve goes to infinity. Okay, let's go with rule number 5. You do the evaluation. If you take this guy here to the left, you have 0. From here somewhere to the right, you have 1, 2, 3. So it's an odd number. From here, we've got 4. So this does not belong to this part of the axis does not belong to our root locus curve. And this area basically here has 5 elements. So 3 poles, 3 zeros. So it needs to belong to our root locus curve. If you only have a delta of 1, we immediately can say that our angle is minus 100, or is plus. It's always plus. It's plus 180 degrees. Okay. So now let's go to the centroid. Okay. Now I didn't pre-compute it, so I need to do it on fly. This guy here has a pole at minus 10. We see that. And if you want to now, I'm going to do it slowly just that you see it once. You obviously need to calculate these poles, right? So it's going to be minus 2 plus minus square root of 4 minus 4 times a times c times 10 over 2, right? Okay, so what is this? This is minus 1 definitely. Plus minus square root of this is roughly minus 36 over 4, isn't it? If you bring that under brackets, okay, this then is minus 1 plus minus 4 is 9, so it's plus minus 3i, right? Let's see, actually we have the result here. 1, 2, this is 5, yeah, it's plus minus 3, right? Okay, good job. Well done. Okay, now let's compute the centroid here. Okay, for the centroid, we again need to add up all the poles, right? Okay, first one, minus 10, and then it's going to be minus 1 plus 3i minus 1 minus 3i. And remember, this is why we actually said we only need to consider the real parts, because we always going to have conjugate complex pole pairs, and this is why this guy is always going to cancel. Okay, so you actually would not have needed to compute this guy, because it will cancel out anyway if you do the centroid calculation. Okay, and then we've got minus, and now the zeros come into play. We've got one at -1 and the other one at -5. Okay, and I'm losing a little bit of space now. And here it's simply 3 poles minus 2 zeros, and the result is -6. So you draw the centroid here, and from here the asymptotes. Actually, if you miscalculate the centroid, actually here it doesn't matter, because we only have one asymptote going to infinity, and it does not matter where this asymptote starts, right? It can start at the origin. We know that this guy only can go left. So when you do a miscalculation here and you say it's going to be -4, -2, whatever, the result of the root locus curve will not change. But here the -6 are the correct result. Okay, so far so good. Yeah, here the main takeaway is really take care when the zeros come into play. You have to consider this minus here explicitly, and yeah, this, if you get sloppy, this is sometimes an area of mistakes during an exam. So really take care of this minus here. Okay, I'm gonna get a sip of water. So the next example is again has 3 poles, but this time actually we have the same. Let me check this. We have the same second order pole pair here, right? So this is the same as before. This time, however, we have a pure integrator, right? Integrator. That means we have a pole. Let's call it pole 1 at 0, right? See it here. The other 2 poles are the same as before, so we know that. And this time we only have 1 0 at -5 here. Okay. Okay. So we've got 3 curves, obviously, because we have again 3 poles, and 2 of those go to infinity, because this time we only have 1 0, so this must be 2. And if you do rule number 5, should be pretty obvious. From here you have 0, from here you have 1, and from in that area here you have 1 2 3. It's also an odd number, and from here you have 4. So this area cannot belong to your root locus curve on the x-axis, right? So this does not. Okay, so far so good. Let's compute the centroid here. I think we call it sigma, right? Okay, so the first pole is at 0, so no contribution here. And then again, this conjugate complex pole pair, we know that the complex part cancels out. And then we have +5, -5, right? The 0 is at -5, so it turns positive. And now we've got 3 - 1. And here you see the first time that actually our centroid is in a right half plane, right? It's plus 1.5. So why does that actually matter? Well, let me get to this in a second. The angles are simply, we have 2 going to infinity, so we know it's going to be 90 degrees and 270 degrees. Same thing as with the PD2 system. So if you go back to our PD2, same thing, right? Really, the angles do not change when you change the location of the pole. The angles really only depend on the number of the poles and the zeros, right? That's why it's always, when you have 2 more poles than zeros, you will always have 90 to 70 degrees. This is kind of a rule. Okay, so why is it important that the centroid is in the right half plane? Well, it's you could say, okay, the result is in the right half plane. Okay, but the important stuff here is that if you have the centroid in the right half plane, you immediately know that there will be a restriction or some problems on your controller gain. Why? Because you don't want to place your closed loop poles in the right half plane, right? Because then you have an unstable system. So if your centroid is in the right half plane, the chance is actually pretty high that at some point you can reach the right half plane when you just take the wrong gain, right? And exactly what we see here. We see here that our system G of S is basically stable, right? But this guy goes left, he needs to go left, and then these two guys need to, the locus curve need to approach the asymptotes. And when you make your gain too big, remember when your feedback, your proportional feedback gain is 0, you're starting here. You increase the gain, you're moving the poles around. And in this case, when you make your gain too big, you're crossing over to the right half plane and you're getting an unstable system. This is basically similar what happened with the espresso machine. When you made your gain too high, it actually goes haywire, right? It goes over all borders. It goes to infinity. And you have seen that with the espresso machine, which was a PD3 system. In this case, we have an, oh my God, we have an integrating system, second order lag, and we have a PIT2 system. Okay, so also this guy at some point gets to gets unstable, and this is kind of a problem because this system per se is not stable, right? Because we have a free integrator, so we need a proportional feedback actually to stabilize it. So this guy moves to the left, then we are stable, but we cannot move the gain up very high because we are immediately crossing over. So the only safe area is basically between here, and this pole here will end up being here, and so it will end up being very close to the origin, making this system, if you just use a proportional controller, pretty slow. For this system, you immediately should think of something else, adding another 0, because another 0 will drag these two guys to the left. Okay? Okay. Actually, I just wanted to show you how to draw the locus curve now. I already did a lot of interpretation in there, but why not? Okay. From the pure calculational point of this root locus curve, I think it should be clear. Last example, actually a little bit of an involved one. So we have 5 poles now, and we have also a conjugate complex pair of zeros, right? Okay, so now what you would need to do is you need to compute all the poles and zeros. Okay, so okay, let's do this somewhere. Okay, the first pole is -5. This zeros here is the same polynomial as we had before. So our two zeros are at minus no, what was it? -1 plus -3i, right? This guy is actually pretty easy to solve. This is actually just mirrored. So if this guy is negative, this means this has the same roots as this polynomial, just the damping is negative, right? So you basically switch over here to the right half plane. So this guy has poles, let's call it 4 and 5. They must be +1 plus -3i. I mean, you can do the calculation, right? But this definitely is the same polynomial, just there's a sign change. A sign change here means we actually mirrored the damping to be negative, so this is an unstable pole pair. Okay, and last but not least, this guy I actually don't know by heart, so I probably need to calculate those. So P2, P3 is -6 plus minus square root of b squared, 36, -4 minus 40. over 2. So this should be minus 3 plus minus square root of minus 4 over 4, right? So it's going to be minus 3 plus minus I. So let's check if this is roughly right. Minus 3, yeah, minus plus minus 1. Yeah, okay. Should be okay. So now we got everything to compute the centroid, right? So then here I need a little bit more space, because this is huge. Okay. So we've got, let's start with the denominator. We've got 5 poles and we've got 2 zeros. So it's a 3 in the denominator. And now let's add up the poles. The poles are minus 5. Then we've got minus 3 times 2, right? These guys. Just doing it, multiplying by 2. And we've got these poles, which are plus actually, right? See? Plus 1 times 2, minus, and our zeros have a real part of minus 1, so we've got 2 times minus 1. And if you do the calculation, what gets out is minus 2.3, which is here, this guy. Asymptotes, we've got 5 curves, right? Because we have 5 poles. 3 of those curves go to infinity, because we have 5 minus 2 is 3. 1, 2, 3, and we need 3 asymptotes, and we immediately know if we have 3 asymptotes, the angles are going to be 60, 180, and 120, 300. Okay. First thing that you then do is you plot in your centroid, you plot in the angles for the asymptotes, and now you're checking. Okay, rule number 5 basically does not help us really this time, because here on the left we've got 0, here to the left, to the right we've got 2, here to the right we've got 4, and the only area which belongs from the x-axis belonging to our locus is this here, because here we finally reach a point where we actually have 1, 2, 3, 4, 5, 6, 7, right? So till here. So we know that this guy goes along the asymptotes to infinity. The others are a little bit more involved. Okay, we know that 2 poles, right, need to go to the zeros. Obviously, these ones go, and these are closer to the infinity, so these go along the asymptotes. I mean, if you would have drawn this like this, then you would have been in trouble to say, okay, how does this go? This usually never happens, such a bad crossing, right? So, but yeah, to be fair, for this example, you would have needed a couple of more rules. For example, there's a rule how this curve goes out the 0, or actually this one goes in the 0, and so on, and how this curve leaves the pole here. But yeah, I'm actually, yeah, I'm not a big fan of this very sophisticated, very mathematical rules, because at the end of the day you need to roughly understand how to sketch a locus curve, because you're going to do it with a computer-aided software at the end of the day anyway, right? So yeah, this is why I think this is the most involved example here. And but yeah, for the calculation part, it's important to really to practice this a couple of times. So if I was too fast, please go over that alone. And there are some examples in the there will be some examples on the server as well, on the root locus curves, to practice this a little bit more. Okay, so some notes before actually we close the chapter, or not chapter, we close this part of drawing the root locus curve. So in case this is, yeah, I need to have that rule there, but you don't remember it by heart. In case you have 2 or more lines going to infinity, the sum of only one f, the sum of all roots is constant when relocating the poles. This is sometimes helpful when you design the controller. But what does that mean? I'll show you quickly with an example. Let's say we have, it says 2 or more lines. Okay, let's take a PD2 system going up there. We know the locus curves look like this, right? Okay, so when you change the gain, the sum of the roots, well, the sum of the roots is, let's say this is -1, is -1 plus minus I times whatever you like, right? Some constant C, or let's call it K. Whatever you put in K, you will end up on that locus line here. And when you add that 2 up, right, it's always going to be, the sum is going to be -1 plus minus AK plus IK -1 minus AK. So this always cancels. So the sum is always going to be -2, whatever gain you select, right? If you set your controller gain to 100, 1000, 1, it doesn't matter, the sum does not change. Sometimes this is helpful for double checking, but honestly, I've rarely used that kind of, in some textbooks you see this as additional rule, but yeah, whatever. Okay, they discussed rules, and this is important now, because especially for flight control engineer, this is important. The discussed rules hold for negative feedback. So we're always assuming the minus in the feedback loop, right? Why is this important for flight controls? If you're listening to at least my flight control course, we know that the aircraft have a very specific coordinate systems, right? And there it can happen that due to the measurement and the coordinate or the sensors are plugged into your aircraft and the coordinate system, you're sometimes actually using a positive feedback. But this is not due to physics, this is simply due to your coordinate system definition, right? You're still stabilizing your system, but you need to do a positive feedback because the sensor gives you a different sign. Bottom line is, these rules I've shown you are for negative feedback, and if you have sometimes happen to have a positive feedback, you need to be careful, because then some of these rules are basically changing. It's not actually that hard. For rule number 5, you're basically looking not to the, you need to look for, either you look for even numbers to the right, or you look for odd numbers to the left, so just the other way around as we're doing now. And also for rule number 8, you're basically mirror the angles around through the centroid. So the rule basically changes. Instead of, let's say, well, for 90 and 270 it's easy. Instead of, if you have, let's say, if you have these asymptotes for negative, change the color, sorry for that. If you have these asymptotes for negative feedback, if you have positive feedback, they're going to look like, or let's do the positive in a different color. For positive feedback, they will look like this, right? They are just mirrored around the centroid, basically. This is all what changes. Okay. Yeah, you need to be also careful, but we're going to talk about that a little bit later on in lecture, when you have right half plane zeros. So if you have a zero here, these zeros may cause you that you have a sign changed, and then you have again need to obey or need to take care of these rules. But yeah, these are very specific problems. Okay. So to get you a little bit more practice, I actually coded up this whole methodology. Okay, to be fair, MATLAB has built-in functions to draw the root locus curve, right? So if you say I have a system I'm doing a project on, or I do my bachelor thesis, which is probably approaching for some of you pretty fast, and you decide to do it in controls or in flight controls or flight mechanics, and you somehow happen to have a transfer function, right? And you want to know the root locus curves because you want to do control, you can always go to MATLAB and draw this root locus curve, right? So there are built-in tools for that. It's just air locus in MATLAB for your system. So you define the transfer function and then you do air locus. However, they are not pretty. They're not pretty actually, right? So that's what I want to say. So I did a little bit of coding to make you a little bit of a nicer illustration and also plot the centroid and so on. In case you do start learning for the exam and you want to create your own transfer function, you say, okay, why not taking a random transfer function? You can always double check with that piece of code. It's on the Moodle server. I actually can show you. You just download. I think this is actually a pretty neat piece of software here. Okay, let's see where. So if you go down, so I'm making a little bit of advertisement for my codes, right? And it's this one here, drawing root locus plots. What I did, it actually comes already with a couple of examples, right? For example, there's one from an old exam in there. You have all these PD2, PD3, with you can choose whatever you like. Let's take this example from the exam. You can put in here your own transfer function. Then you just let it run. Now let's hope that it works. This is the transfer function. So we have a couple of poles on the right and left half plane. We have two zeros, and what the takes some time now. What the function does, it plots you here. This is the standard MATLAB plot, just with a little bit brighter lines. And what I'm going to do is then I'm going to zoom in so you really can check it. And finally, it also shows you the centroid and the asymptotes. So if you do some examples on it, by the way, you can check all the examples on the server with that file, right, on your own if you did it right. It actually, if I'm drawing the centroid and the asymptotes, it also calculates them, right? So you can get all this information directly out of that file. So I hope it is for convenience that somebody, if somebody wants to use it, feel free to download it and use it. Okay, what time do we have? 12:45. Okay, half an hour to go. So next part, actually we are building up on that now. We now know, actually I have a storyline, right? Yes, I do have. What we want to do next is we actually want to get closer to the part of control design, because at this point we have to be pretty lucky, right? Why? Well, we have a system and we know how to draw the root locus curve for that. And we need to be pretty lucky that we have a point in mind we want to place our closed loop poles at, that and only if these points are on our root locus curves, we can design a proportional controller, right? And I guarantee you 99.9% of the times the point you desire will not be on your root locus curve for just a proportional feedback. But that's no problem, because we can add dynamics to our controller and thereby move the root locus curve around. And how are we going to do this? This is what we are going to develop next. Okay, but step by step. So before that, okay, let me get you the big picture here. Before that, the goal is to design controllers and make our root locus curve go through the desired point, right? Directly presenting you that would be too fast. So what we're going to do first is we're going to do mathematically check if a certain point is on the root locus curve, right? Let's say you have a system and you don't know the root locus curve because you don't have MATLAB. And your professor tells you, okay, design a controller that your closed loop poles are on that point. First thing we could do is we could check if this point is actually reachable by a proportional feedback. So we're going to check an arbitrary point if it is located on our root locus curves. Okay, I have, I think, 3 examples there to do so. Okay, but let's see where we are. We know how to, or actually we know that the closed loop poles move along certain curves, which are the root locus curves, if we have proportional feedback. And we know at this point how to sketch these curves, right? This were the examples we had before. What do we actually want now? We want to design a controller based on that, right? So this is the goal. How do we get there? First, we need to discuss, we say we have a certain point in mind, and we're going to check that if that point is on our root locus curve. Unfortunately, most of the time in practical examples, the answer will be no. But it's crucial for your understanding that you know how to do that. And if we have done that, then we can trace that back and design actually a controller. Okay, so let's do it. We're gonna. I thought about this a long time, and I realized doing this by examples, by dedicated examples, is the best way to go with. So I've given you an example G of S, right? It's a very simple system. It's a PD1 system with a time constant of 0.5 and a static gain of also 0.5. So what we want to do is we want to take the G of S, we plug a proportional feedback around and design a controller. The question we always have is where to place our poles at, right? This guy definitely has a pole, right? The open loop pole is at -2, but maybe we want to place that somewhere else. And now we're going to check if that location we desire is actually reachable by just a proportional feedback. Okay, so let's determine the closed loop poles, right? So let the closed loop poles again take the controller into account. So we need to take that into account as well. And we know that the closed loop poles are nothing but the numerator plus Kp times our denominator of that equation. If you plug that in, it's going to be S plus 2 plus Kp times 1, right? Because here's a 1 is equals 0. Okay. I already give you the solution of this root locus, right? So this is the root locus curve. The pole is at -2, and if you increase the gain, it moves to the left to infinity. Okay, so far so good. We know that. That's not actually that hard. What you would usually do, you would usually select a gain. Let's say you take the gain at 5, and if you put the gain Kp to 5, you realize the closed loop pole is going to be at -7, right? S plus 2 plus 5 equals 0 ends up being a pole at -7. So far so good. But this is usually not the way we want it to have, right? We don't want to select, I'm taking a gain of 5, I'm ending a pole at 7. Take a gain of 100, I'm ending at a pole at -102. This is not the way you want to design a controller. You want to say, I want to have a pole at -10. What gain do I need? Actually, you can do this here pretty easily, but here it's easy because it's a PD1 system. So, if I tell you, place the pole to -1, can you reach that with a proportional feedback? Your answer would, for this example, be immediately no, because you look at the pole 0 plot. But can we check that mathematically, right? So this is how we want to do this for this example where we already know the solution. So we are considering 3 points. The first point is point A. It's at -4. This would mean, okay, for this example, we want to shift our pole from -2 to -4. Clearly, we see that this guy is on a root locus curve, so this point is reachable. Okay. Point B is -1, and it seems to be that this point is not reachable here. Point C is up here. Also, should be clear to everyone, with pure proportional feedback here, we cannot reach that point because we are moving with proportional feedback along that line. Okay? So these are already the results. But the thing is, what this equation tells us is that if we select a certain gain, we get out the closed loop pole. Now what we're going to do is we're going to select a certain pole for S and calculate the gain. Okay, so we're doing it the other way around. So instead of injecting the gain and calculating the pole, we are inserting the pole and calculating the gain, right? And actually we have done this when we actually, we have kind of done this when we did the pole zero cancellation. We basically partly defined the pole by saying we want to have a damping of 0.6. This is also defining a second order pole pair, just one part of it, right? A pole pair has a real part and an imaginary part, or it has a frequency and a damping. This goes hand in hand. So if you define only the damping, you're basically setting one part of the equation. Nothing else we're going to do here. We want to compute the gain for a desired pole location. But we already know that we will have some troubles here because the gain will at least be not what we expect, because we cannot reach it here. We cannot reach the point with a negative feedback. So what happens if we insert that point? Okay. So let's check point A. So point A is -4, -4. It's real. Okay. So let's put this point into our equation here. And the equation I'm talking of is this one, obviously, right? So this guy here, S plus 2 plus Kp equals 0. So let's put in our point A, -4 plus 0. It's real, so the complex part is 0, plus 2 plus Kp is equal 0. So if you do the computation, you get out a Kp of 2. So this is trivial, right? This should be doable for everyone. If I give you a PD1 system and say, please place the pole to -4 in a closed loop, you should be able to compute the gain to do so. This is what we have done here. Obviously, you can ignore this part because -4 does not have an imaginary part. But for now, we are holding the result is real and positive. And it's a value of 2, rising. Means if we select a gain of 2, we place our closed loop pole at -4. Okay, so now this was kind of expected, that the result, because we know that this point is on the root locus curve. So now let's go with this point here. Okay, so let's go -1 plus, again, it's a real number, plus 2 plus Kp equals 0, okay? And if you do here the calculation, it's -1. So what changed now is the sign of this gain here. Suddenly we get out a real negative gain. So, and what that means basically is the following. You have G of S, you have your PD1 system, and you need to have -1 here. And now see what happens. Right, this is what we get out. And this is equal then putting a plus here and a plus here, right? If you consider that to be 0, right? So this is the same. So what it tells us that we only can reach this point B if we do a positive feedback. And if you look at the rules I've shown you, if you do positive feedback, the root locus curves look like this. And this is fully understandable, actually, because what happens when we do negative feedback? When we do negative feedback, we are stabilizing our system, right? We're making it faster, we're making it better, so to say, in terms of stability and performance. We are moving that guy to the left. The time constant gets lower. We are moving away from the area of instability. If we do positive feedback, we are making our situation worse. We are moving towards the area of instability. Here, we are making our system slower. And I always told you, usually positive feedback is not a good idea, except it comes from the coordinate system like flight mechanics. But usually, It's not a good idea. And this is what you see here. So if you want to make your system worse and make it slower, you basically need to have positive feedback. You want to destabilize your system. This is the outcome here. Okay, but still, we could design a controller by just changing the gain, right, for that point. Okay. Finally, we take our point C. Okay, what C was a conjugate complex pole location, and it was at -2 plus J. And then we have +2 plus Kp is equal 0. So, and what we get out here is Kp equal -J. Okay, so we need a little bit a strange controller. And I hope you agree with me, such a controller you cannot implement, right? It's just a complex number. It's pretty hard to code this guy up, right? It's just, but what it tells you is basically your gain is -J. So it has to have somehow look like a complex number. And a complex number is kind of a dynamical system, right? So instead of a pure gain, we now need to add some dynamics. That would be the interpretation. To make that point reachable, we need additional parts in our controller. For example, in this case, I probably would recommend another pole, then this point will probably be reachable. Okay? It doesn't matter. For us now, it only counts when the outcome is real, right? Because if it's real, we know we can reach it. If it's not real, if it's complex, we know we cannot reach it. It does not go through, right? Our root locus curves. Okay, so that means if this Kp, if the required gain is a complex number, it simply tells us we are not able to reach that point with a proportional feedback. Because if it would be reachable by a proportional feedback, the gain needs to come out real. It does not. If it does not, if it's complex, it's not reachable. This is the only information we are extracting here. So the strategy at this point would be, if we want to know if a desired point is on our root locus curve, we just take that point, we plug it into our characteristic equation, we compute the proportional gain. If this gain is real and positive, it's definitely going to be on our root locus curve. If it's going to be real and negative, we need to change the sign. We need to destabilize it. It's probably not a good idea. And if it turns out to be complex, then it's not reachable, right? So the problem with this method is it's going to be a little bit tedious, so a little bit exhausting if the order of the system changes. So if you, in order, I mean, if you don't have a PD1 system here, let's say if you have a PD5 system here, you always need to solve like a polynomial of fifth order. And this is not a good idea. So it's this strategy, inserting the point and calculating the gain. Yeah, it's nice to show you what I mean with that, but it's not gonna work for big system because the equations are just gonna be too big, right? So it's one thing which helps here is that we move over from the conjugate complex plane to actually to the polar form of a complex number, because you know a conjugate complex number has a real part and has an imaginary part, while in the polar form we are more thinking of angles and amplitudes. And the advantage here is that we can add angles and just add amplitudes together. So we take this step and then I'll show you the criterion. Okay, where's my slides? Okay. So we know that Kp can end up being complex, right? And it's not good if it ends up being complex, but still, the fact that it can be complex makes sense to get to a point where we actually rewrite our Kp in terms of a magnitude and an angle, right? So Kp has a real part, has an imaginary part. We are simply rewriting this guy instead of real and imaginary part to an amplitude and an angle. And you know this from basic math how you do it. You take a Pythagoras and you're basically computing. Say you have a complex number, it has a real part, it has an imaginary part, and instead of real part and imaginary part, you're basically saying, okay, it has a magnitude and it has an angle pi. This is all what this means, right? Okay, but now let's take on this complex, pretty general formulation of our Kp. So what did we say about Kp? We said Kp needs to be real. If it turns out to be real, we can reach a specific point we desire in the root locus plane, right? This is what we said. What does that mean for our Kp in polar form? Well, the fact that it needs to be real means that the angle needs to be 0 or 180 degrees, right? Because if this angle here, see, let's go with green. If this angle here is 0 degrees, so if this one is 0, you're only having a real number. If it's 180 degrees, you have a real number which is negative. Okay, now we can finally formulate actually a criteria. So if we want to check a real, if we want to check a point, if it's reachable or not, we simply calculate this feedback gain in polar form. And you will see in polar form it's much easier. And now we can say the criterion for the angle of our Kp is the following. I think I named it phi. If the angle turns out to be 0, right? I will fix that in a second so that it fits your script, but it's easier that way. Then we know that Kp is bigger than 0, and this means we have negative feedback. Sorry. Not this again. Sorry for that, lacking space. Okay, so if Kp is real and positive, our angle needs to be 0, right? Because otherwise our Kp is not real and positive. So unfortunately, it's not going to be only 0. It also can be turned around 360 degrees. So it's basically 0 plus 2 pi times n. And this obviously is just 2 pi times n. This just means that the angle can be 0 degrees, 360 degrees, 720 degrees, 1080 degrees, and so on, right? If the angle is that way, you know you can reach the point. If the angle is minus 180 degrees, then we know we're going to have negative feedback to make this point reachable. So that means, sorry, positive feedback, not negative. So we need to change the sign. And obviously the same goes here. Instead of minus 180, we write it in radians, which is actually plus minus. It can be 180, it can be minus 180, it can be minus, oh my gosh, 540, it can be plus 540. So what we do right is it can be pi plus 2 pi times n. Actually, you can also write plus minus because it can it can also turn in the other direction, right? So it just needs to be a multiple of 0 and a multiple of 180, right? This is why you need to come up with that strange. Actually, in the original form of the script, I only had 0 and 180 degrees, and then I created an example. It turned out to be 540, and I was screwed. So I decided now to fix that here and actually show you it is 0 degrees or 360 and so on, right? Okay. This here, this is just this justification which I actually showed you here. Okay, so where are we now? We have now actually rewritten our criteria in polar form, right? This is all we've done so far. We said, okay, if the gain turns out to be positive and real, we know that the point is on our root locus curve. We said this can get a little bit tedious when we move to a very complex system. So it's better to move to polar form, because if you have a lot of poles there, you can just add the angles. But I'll come to that. So we have now defined the criterion for what our gain should be, right? In the polar form. One problem though is we still need to take our point and insert it in g of s, and this is a little bit of a problem. So the workflow would be take the desired point, put it in the characteristic equation, calculate Kp. So these are three steps you need to do. Okay, maybe there's a different method, and yes there is, and I'll show you that. And actually this method, I know the derivation takes some time, but can be evaluated pure graphically. Okay, so let's take on our characteristic equation one more time. We said our characteristic equation is nothing but 1 plus Kp times g of s, right? This is the, when you close the loop, this is your denominator of your closed loop, for example, of the complementary sensitivity, right? Okay, now let's express g of s here. G of s is nothing but minus 1 over Kp, okay? And now we are inserting the polar form for Kp, okay? G of s, Kp, we said, okay, has an amplitude, which we named Kp bar, and it has an angle. And instead of the angle phi times j, we're simply writing minus phi times j, right? Because it's inverted. Okay? So, and this is actually now crucial for the understanding what we're going to do next. So instead of taking the point and inserting it into the characteristic equation and checking our Kp, we are deriving something where we only need to check g of s. We don't care about our gain anymore, because we now know what's actually standing there. We say, okay, remember we said Kp needs to be real. And what this equation tells us, okay, g of s needs to be the negative inverse of the amplitude of Kp and the angle. So instead of checking our controller gain after solving the characteristic equation, we can derive something where we only need to check g of s. And g of s needs to have an angle which is the same angle as this guy here. And this is our gain, right? So let's see what the right side is doing to our angle. Okay, we have an inversion of our gain, and we have here, okay, the negative gain, right? So let's see. And this is now pure mathematics. Inverting a complex number basically mirrors the number around the real axis. So if this is your complex number here, and you invert that, so you take e to the power of phi j and you invert it, you basically come up with this one. But remember, we say our gain needs to be real, right? And if it's real and if we invert it, it does not change the angle here, right? Because if we have something like this, we are assuming our gain needs to be real. We are inverting this. It's basically not changing the angle because the angle is 0. So there's nothing to change here. Obviously, it would change the amplitude, but let's assume now the amplitude is 1. Okay, what happens if we multiply a complex number by -1? Remember, we are multiplying this one here by -1. Well, you're changing the angle by 180 degrees, right? So if you take this guy, multiply it to -1, you're basically, this is your result. You're changing the angle. Okay, what does this have to do with our criterion, right? You could say, okay, we have a nice criterion for our gain. We know that the gain needs to be positive, meaning that the angle should be 0. But remember, we don't want to check that gain because we need to compute that gain. We need to solve the characteristic equation. And this is actually not what we want to do. Instead of checking the gain, we now have actually already derived something where we only can check G of S, right? Because, see, here what this guy says, okay, we know what the criteria for KP is, but now we are taking that criteria and put it over to G of S with this pure, very simple mathematics. So instead of checking our KP, we are checking now the angle of G of S. And the angle of G of S needs to be the inverse, the negative inverse of the angle of KP. This is exactly what is standing here. And if you do that, you simply need to change this whole thing by 180 degrees. So remember, we said our gain needs to be real. It needs to have an angle of 0 degrees. Taking the last slide means exactly that. You need to take your system G of S, and the angle of that system to that specific point needs to be minus 180 degrees. This is all what it says. So now we can formulate a new criterion, and this criteria simply is we only need to take G of S. We don't compute KP explicitly. We only take G of S and see what angle G of S has to that specific point we are desiring. And this is actually pretty cool, because we never need to solve the closed loop. We can just take our system and compute the angle to that point. And if the angle turns out to be 180, we know, 180, we know this point is reachable without computing the gain, without solving polynomials, right? So we have now a criterion on the angle of G of S, and this needs to be simply 180 degrees plus, again, if you turn it by 360 around, needs to be 180 degrees for negative feedback, and it needs to be 0 or 360 and so on for positive feedback. So the only thing what changed here is 180 degrees. Why that changed? Well, because we did an inversion, right? We have and we have the multiplication by -1 here. Sorry, not the inversion. The inversion doesn't change. We have this multiplication of -1 here, which is exactly here. So instead of checking KP, we are now checking G of S, and this equation tells us, okay, that G of S needs to have 180 degrees different angle than KP. If this is the case, we can reach the point. Okay, so now you should say, okay, what I have to do now is I have to take G of S and insert my point in G of S and then compute the angle, right? And you know how to compute the angle. It's just, again, going to be a complex number, whether it is in polar form or in absolute coordinates. Yes, this is what you have to do, but there is a pretty simple method to do so. Namely, this method is completely without actually computing the transfer function. It can be evaluated fully graphically, and this is what we're going to close this morning lecture with. So it's actually pretty simple. So instead, if you have a system and you have a specific point, right? And I show you that on the next slide for our example. You only need to compute the angles between all the zeros and all the poles. So you don't need to put your desired point, I named it as A, in your system and compute the angle. No, this is basically a graphical evaluation you can do. And this is shown on the next slide. So, by the way, the proof I'm not going to show you. You can find it in the textbook. So, this is your PD1 system, right? PD1. And now you want to know, can I reach this point, right? Is this point reachable? Obviously, it's not going to be reachable because if you compute the gain now, it will be complex. This is what you can do for this example pretty easily. But what we are going to do is we're going to compute the angle. And the angle is simply this guy here. sorry, not this one here. It's anyway, this angle here. So you go from the point to the point and you compute this angle, and you really see this guy is not 180 degrees, right? So this point cannot be on your root locus curve. So what you graphically need to do if you have a more complex system, you just take the desired point and you calculate all the angles, and then you sum them up. And you sum them up if it's a zero. So let's say you have a zero here, right? This would be your angle. You can actually measure it with a ruler, or you do a Pythagoras. You take that angle, it adds up positively, and if it's a pole like this guy here, you need to subtract it. And the result should be, if the result is 180 degrees, you know you can reach the point. This is all what you have to do, right? So no complex computation of your transfer function with complex numbers. It really gets down to basic mathematics, basic drawings, and the maximum what you need is a little bit of understanding of triangles, right? This is all you need, and what we're going to do. I think there is... Okay, there's one more slide I want to hop through, and then we're going to finish. Okay, so if you have an example and you want to know if a certain point is on your locus spot and you want to do the computation, you just measure the angle between all your poles and zeros to that point. You sum them up, and if the result is 180 or minus 180 or minus 540 or plus 540 and so on, it's going to be on your root locus curve. That's it. Okay, so you could now say, okay, wait, we have the point where we also did the computation of a gain, right? So I still need a gain. So what happens if the answer is yes? What's the gain then, right? So I still need a gain for my controller. Well, the thing is, yes, you can compute the gain, right? Remember our condition, g of s needs to be equal minus 1 over k, the amplitude of kp times the angle, okay? And this time, what this says is, okay, the amplitude of g of s needs to be the inverse of your kp. So what you now can do is you just compute the magnitude of g of s, you invert that, and this exactly gives you your kp, right? Don't be scared, we're going to do this as an example. So now you could say, okay, what happens if kp turns out to be complex? I tell you, no, this will never happen, because you only will compute this kp if your angle turns out to be 180. And if the angle turns out to be 180, that means your gain needs to be real. If it's not going to be turning out to be 180, you don't need to compute the gain, because you know immediately you need to add dynamics to your controller. Otherwise, you need a dynamical controller to reach that point, because the point is not reachable. So to judge if a point is on the locus curves, you only need the angle criterion. And if this is fulfilled, then you can compute your controller gain, right? Okay. I'm going to finish there, and I'm going to sum up the procedure in the second part of the lecture, and then we follow up with some example, and we will be able to finish up this whole discussion on the root locus curve today. I know this has been a little bit mathematical, but the outcome is actually pretty exciting, because the outcome is simply we only need a ruler or a Pythagoras to validate if we can reach a point in the root locus curves or not. And this was a big finding in the 50s, that you actually could do this whole computation of a controller on paper. Remember, they didn't have any computers, with very simple mathematical algebra. And I think this is where was the point where this whole theory also opened up to a broader field of engineering, or broader, more engineers, because I think this is actually pretty well understandable and not going into the deep world of mathematics, right? But we have to understand this derivation once and for all, and then it's set. Take care and see you later.